water heater technologies and grid connectivity. I'm Bill Healy. I'm from the National Institute of Standards and Technology, and I'm the moderator for this session. We'll start the webcast, a few housekeeping announcements, and then we'll quickly move into our speakers, followed by a little time for Q&A. As a reminder, your screen is customizable utilizing the various widgets found at the bottom of your screen. Presentations can be downloaded as PDFs from the resource list in the menu. Attendees are in listen-only mode but can submit questions through the Q&A box anytime during the webcast. Presenters will be answering questions following all of the presentations. All presentations will be available for on-demand viewing within a few days on the Engagement Hub. I want to point you to the Zoom discussions that will open at the end of the webcast to continue the conversations and allow for additional questions. I encourage you to take a look at that link that is in the chat box before we go. Click on the Zoom widget or download the daily Zoom link PDF available on the Engagement Hub. Please be sure to complete the forum survey after your last webcast. It helps ACEEE in planning for future forums. And ACEEE would appreciate your feedback regarding this year's Hot Water Forum. You will have access to the survey link in all of this week's sessions on your console. Please take a moment after you watch your last webcast and complete the survey. For those that do, you'll receive a $25 discount off your registration for the 2022 Hot Water Forum in Atlanta, hopefully in person. And last, we want to thank all of our sponsors and our partners for their support of this Hot Water Forum. We really couldn't do it without. So now I'd like to introduce our distinguished panelists for this session. They are Amruta Kanolkar from the New Buildings Institute, Tanya Barham from the Community Energy Labs, Tristan DeFranville from SkyCentrics, and Ebony Mayhorn from the Pacific Northwest National Lab. We'll start with our first speaker. Amruta is a project manager at New Buildings Institute, and her expertise includes energy efficiency, decarbonization, and demand response management to improve the performance of the built environment. She has spent more than a decade working to transform the built environment through energy efficiency programs, best practices guidance, and emerging technologies development. Amruta has a master's degree in energy efficient and climate responsive built environment from Arizona State University. Amruta will speak on emerging heat pump water heater technology. Amruta, I turn it over to you.
Thank you, Bill. Thank you for the warm welcome and the introduction. Hello, all. So I will be going over emerging and grid-connected heat pump water heaters, give you an overview of that. This work is part of Advanced Water Heating Initiative. So just a little bit about the initiative. It's a market transformation initiative to help increase the production and adoption of heat pump water heaters. And it's a collaborative effort of over 50 organizations. You can find more information about the initiative at the link below. I wanted to give you a quick context. My slides are moving backwards. Okay, so just a little bit, a quick context of the current water heating stock. So over 90% of the water heaters in California and 50% in the Northwest are directly pumping fossil fuel for heating water. If you look at the national perspective, which is the graph in the center, it's about like over 54% of the water heaters are fossil fuel dominant. And if we were to transition all of these water heaters to heat pump water heaters, they have the demand response potential of over like 20 to 40 gigawatts. So just this technology has a great potential to be a grid battery. So in my next few slides, I will be giving an overview of the emerging residential, multifamily, and small commercial heat pump water heater technologies, and then later on, like tied back to grid connectivity. So what you see on this screen is the residential unitary heat pump water heater manufacturers and their technology features. So the voltage, the grid connectivity aspect, and finally the refrigerants that they use. So to focus our conversation on emerging technologies, what you see in the green are the emerging technologies. The 240 volt are in the market for decades, but the 120 volt retrofit-ready heat pump water heaters are just hitting the market. And there are 4 manufacturers. They are like between now and end of 2021, they should be out with all the technology, all of the 120 volt products. So now a little bit about why retrofit-ready heat pump waters are even needed. So what you saw in my first graph, there is about 54% of national water heating stock, which is carbon intensive. If they want to decarbonize or if they want to switch to heat pump water heaters, the only way for them to do it right now is to go for expensive and extensive panel upgrades. So if this technology is validated, they will no longer need that. The 120 volts retrofit-ready are going to be, they can be plugged into any existing electrical outlet. And to validate this technology as part of Advanced Water Heating Initiative, currently New Buildings Institute is leading a field study development, which is going to focus on whether this technology can provide adequate hot water, or rather, which end users this technology provides hot water. Note that the technology so because it is going to be on shared circuit, it won't have electrical like this, the supplemental heat available. So it will be focused on the user satisfaction. The study will be focused on the user satisfaction, energy performance, and installer experience. So what you see on this slide is all these technologies laid out, and with focus, like I wanted to again focus your attention on grid connectivity. All of this emerging technologies, also the current 240 volts are all grid connected. And again, it has more information, but I won't dive into the details. Keep our conversation focused on grid connectivity. Now switching to like multifamily and small commercial central heat pump water heaters. Again, similarly, what you see is multifamily, like central heat pump water heater manufacturers and some of their technology features. So which is grid connectivity, whether they have low refrigerant or the refrigerant type, and the packetized skid mounted approach, and which I will go into the details of that later in my later slides. But so if you look at most of the main manufacturers are coming out with grid connected and lower GWP, global warming potential refrigerants in 2021. Similar information focused on the grid connectivity aspect. There are about 4 manufacturers coming out with these units in 2021. So this is where I wanted to go over the emerging technologies which are planned to be packetized or skid mounted. So at least 2 manufacturers in this year are coming out with this packaged approach, and as part of Advanced Water Heating Initiative, Ecotope and BPA is working closely with them. So the whole approach is going to be like the compressor, the mixing valve, and the storage is going to be factory installed on a skid. So it's much easier for market adoption with such an approach versus the current customized designed approach. And they are going to be, the units that are coming out, they're all going to be load shift. They will all have load shifting capability and with global low warming potential refrigerants. So now the few slides focused on grid connectivity. So as part of the Advanced Water Heating Initiative, New Buildings Institute, we focused some analysis on heat pump water heater and all the conventional water heating technologies, which is electrical resistance water heater, gas tank water heater, and tankless water heater, condensing tankless water heater. And what we observed that, so the green bars here is the emissions, which is about, compared to any conventional water heater, 3 to 4 times lower emissions with heat pump water heaters. And if we start talking about operating costs, with optimized operation and grid connectivity, heat pump water heaters can have similar operating costs to a condensing gas water heater, which is critical to understand because from a customer's perspective, operating cost is equally important compared to emissions or energy. So on this slide, what you see is, heat pump water heaters as grid batteries or thermal batteries. So heat pump water heaters have potential to switch like 0.5 kilowatt of load to off-peak hours. And just to give you some context, there are about 118 million water heaters, just residential water heaters nationally. So just think about the potential these water heaters can have if the market is transitioned to them to act as grid clean and thermal batteries. The slide also shows like how much time it takes to like store the water or use the water. Moving on to just to give you some overall like overview of where the policy is going from grid connectivity perspective. So Washington recently adopted a regulation which requires all the electrical water heaters to have CTA-2045 universal communications port on them, starting 2021, and Oregon is following them. California also adopted JA-13. I will go over the details of that in my next slide. Energy Star recently came out with their specification version 4 with focused approach on the connectivity criteria. Similarly, NEA's Tier 3 and Tier 4 specifications require CTA-2045. And Advanced Water Heating Initiative recommends CTA-2045 and an optional vendor path for grid connectivity. So just a little bit about where California is going. So they recently adopted JA-13, which is a demand management specification in their Title 24, which is the buildings codes and standards. It's a compliance credit for Unitary residential water heaters, heat pump water heaters. All the water heaters are required to be grid connected either through remote demand management or through local demand management, which is activated through time-based load shifting. So, so I would like to conclude by summarizing that emerging and grid-connected water heaters are ready for prime time. Carbon-intensive base plants are going offline, and distributed energy resources are coming online. So the grid requires more flexibility, and smart grid-connected heat pump water heaters have tremendous demand response capability to shift load to off-peak hours and act as thermal clean grid-connected batteries. And with that, I would like to thank you. What you see on the screen is my email address. Please feel free to ask me more questions or get in touch with me. Thank you.
Thank you very much, Amruta. I do appreciate it. All right. Our next speaker is going to be Tanya Barham. Tanya has been an active participant in the formation and growth of a number of new energy technologies and business models, including solar PV, energy efficiency, virtual power plants, grid edge technology, and optimization. Since 2016, she has been a thought leader in the intersection between distributed energy resources, transactive energy, and their role in community climate mitigation. Tanya has extensive experience managing complex energy technology projects and programs, including the oversight and management of multidisciplinary project teams, subcontracting and drafting of partnership agreements, procurement and reporting for government, utilities, and private entities on multi-million-dollar technology contracts. Tanya will discuss water heater as storage. Tanya, I turn it over to you.
Hi, thanks. You have some great presenters today, so I just wanted to say that right off the bat, acknowledge that this might be one of the least sort of technical and data-driven presentations and a little bit more of a thought exercise, not because there's no data, but because I don't have it on a big enough scale yet to release it. So this is some of the data you're going to see here is from a participant's perspective or a community member's perspective within a broader sort of initiative. Why do we care about demand response? What's driving that? And then what other policies are making it so that water heaters look so attractive? And then when we think toward the next step, beyond just traditional demand response programs, which tend to be based on traditional critical peak pricing. So a lot of these demand response programs right now are typically administered over, maybe 5 periods per season at 4 hours at a time. As we start thinking toward future issues on the grid, what I'm really going to challenge folks to think about is the role of water heaters as storage within a whole suite of connected load devices in facilities, and specifically talking about retrofits. I thought the MBI Amruta's presentation was a really great lead-in to talk about some of the implementation issues and some of the driving forces that even are leading us to look at water heat demand response. A big one of those is the push for decarbonization of buildings and transportation. And when we talk about electric vehicle transportation, on one side, we're really talking about building electrification, because most electric vehicles are currently, unless it's public infrastructure, will be behind a panel or behind the meter. So behind the meter electrification is a huge push on one side. And then on the other side, where water heaters have traditionally fallen in the typical demand response, is on the utility side or the grid side. So on the grid side, we're trying to decarbonize the grid, get rid of baseload generation, aggregate demand flexibility at a wholesale level, right? And then on the other side, we're electrifying buildings and transportation and really hoping that that bridge meets in the middle. But what we're finding in the field, and I think Amruta pointed to this when we look at how this is implemented, particularly in retrofits, where, for example, in California and in many commercial environments, 93% of water heat and space heat is gas. So if those buildings are going to be converting to electric in the next decade, as most deep decarbonization studies adopted by communities and municipalities suggest, it's going to pose some pretty big problems, and not at the wholesale level where we're currently trying to manage all these water heaters, but at the distribution level. As we begin to see net zero housing requirements don't just include grid connected water heat. This is also happening in the context of building electrification and net zero. So you're going to begin to see a proliferation of electric vehicle chargers, which can increase the ampacity of a circuit by as much as 30%. You are going to start seeing troughs from solar output at times when there's not enough demand to sop up that solar electricity. So the duck curve that you're seeing in California creates little ducklings at its section of the distribution infrastructure. And then as you begin to see this retrofitting of space heat and water heat, as well as an increased adoption of building cooling on the electric side, you're going to see this real change in the real-time power profiles and load profiles of buildings. And in particular, about 28% of US building floor space is schools, municipalities, and other commercial places that run their systems a lot like how residential do, but with much more complication in how they fund these projects and the scale of the impact that those have. So I'm going to talk a little bit about that today, and how water heaters can play nice with some of these other electrification initiatives in order to deliver not just value to the grid and to get out of our sort of thought just of water heaters, which are an amazing, cool, and very scalable way to manage at grid scale, but increasingly to get people to think about how they can play nice for building owners, deliver value to the building owners themselves, and be able to speak to the building owners about why that generates value, and to the communities that are requiring electrification of buildings in the first place. So what many of us might know is that, these net zero, these all electric building codes and net zero building codes that are being adopted, of which CTA-2045 and grid connected water heaters are a part, are really meant to sort of take this load shape, that includes water heat, but it also includes space heat and vehicle charging, and to change that load shape so that more of it is powered by renewables. Now, I somehow messed up on my slide, and I did have a solar load shape here, but what you would see is that this solar load shape really peaks in the middle of the day, let's say. We could add a wind load shape too, but for most grids, you're talking about still wind here, solar here, and then in the evening, anything that falls outside of those curves is really primarily being powered by gas turbines or coal-fired generation. And, you know, I'm working on resource adequacy for the Oregon Solar and Storage Association. There's really not the capacity right now for solar, storage, hydro, and wind alone to replace necessarily that 14 gigawatts of retirement that's happening just in the Pacific Northwest. So we really need to also start looking at time-varying prices and responsive devices with a way to also not just do that at the grid scale, but with a way that respects the fact that the ampacity of the building and the demand charges that the customer will have to pay are also an important factor in retrofitting those buildings with all electric loads. So water heaters are coming in that wider context of needing to change the building load shape in general, needing to be able to put that building on an amp light diet so that those retrofits are not cost prohibitive for the many, many buildings that need to retrofit, and so that the ongoing operation of that building, and if you look at, for example, schools, municipals, public buildings, churches, these are places that can be spending up to $3 million a year on energy, 10 to 50% of which is demand charges. That's not volumetric energy. That's actually peak demand. So we need to be looking not just at overall energy shifting or the amount that water heaters can contribute to that shift, but also how they play into moving the overall peak and how that benefits customers in terms of reducing their overall peak demand and demand charges on their bill, in addition to helping us move toward a system where we don't have to do as many distribution upgrades or panel upgrades in order to accommodate this electrification. So one of the things that we're looking at, and I'll be showing you sort of a sample size of one right now, but this is one building that is actually part of the BPA studies and the PGE CTA-2045 studies, and how we use CTA-2045 to solve this bigger problem of electrification and decarbonization of buildings. This, you will be hearing in the next couple of years, much bigger studies with much more endpoints, but this is just one point to get you thinking. So here we're looking at a system that uses CTA-2045 as one of a number of connected devices at the user facility. It's a series of sensors, so occupancy sensors in order to shift heating and cooling when rooms are unoccupied for HVAC, HVAC sensing through smart temperature sensors, and other connected appliances like pumps. So basically anything that's heating or cooling water or air is going to be a big draw on electricity. Anything that is electrifying buses, and then any storage is connected to this. At the edge is a hub that uses model predictive control to anticipate or learn the load shape of the building and understand the flexibility of each device within the preferences of users. So this is really important because, you know, water heaters, part of the reason too that utilities love water heaters is most folks aren't going to notice when you're heating or cooling their water. Maybe they won't even notice when you shift a refrigeration duty cycle or another type of appliance. But once you start messing with heating and cooling, now the fish are in the fishbowl and you're going to have much more overrides. So as we start to look at how the whole portfolio of devices works in a building to enable us to do things like preheat and pre-cool without treating each of these devices separately, when we look at the building as a whole, it's worth more than the sum of the parts. However, because now some of the devices that we're playing with really impact user comfort in addition to decarbonization and ampacity of the building, user preferences have to be factored into that intelligence. So part of the studies that we're looking at right now look at how sensitive people's demand flexibility is with the aggregation of these devices based on their stated preferences. So for example, if someone has an oxygen tank or they have backup power and they need to maintain a certain state of charge on the battery, that means we're going to have less flexibility than a building that has battery and EV that we can move around whenever we want. If saving money is a big initiative, we want to check in with people and say, if saving money is a big motivation, are you willing to sacrifice some comfort at times in order to reduce that bill? And in the case of water heat, we say, would you take a cold shower? But in space heat, it's more like, can you deal with half a degree centigrade? And how does having a really flexible device like water heat allow us to then take less draconian measures when it comes to some of these other devices? So one of the things being integrated in these studies are a few different profiles of users and how those user profiles interact with a suite of devices in order to allow us to generate more flexibility at the edge when we manage all of them together as a unit. So this also then is something it's called model predictive control. It's a very new type of control technology based on data-driven, not just data-driven black box data models for model predictive control, but a sort of data-driven model that mimics physics-constrained typical building energy modeling, but requires far less manual setup and calibration of the model because data is driving that calibration and setup of the model. However, the model is being penalized for providing non-physical outcomes. So in these particular cases, what we're trying to do there is to continue to update this physics mimicking black box data-driven model to incorporate devices like water heat to create a solution that's modeling the building and trying to optimize its operation and learning more about how user preferences, the devices, and time varying rate signals interact in order to get better operational control. And operational energy in the life cycle of a building is 70 to 80% of that building's total life cycle energy use.
Hey, Tanya, so we have about a minute or two left, FYI.
Great. Thank you for letting me know. So this is just to show a couple instances where CTA-2045 was used on the water heater specifically. So this is just showing the water heater control using CTA-2045 shed commands. Those shed commands were extended daily beyond the typical demand response period to try and make the snapback of the water heater happen when this was solar rich. Now, this is in Oregon in August. You can see the snapback happening here with the water heat, and you can see how those align with the overall solar profile of the building, and that we've taken those spikes out of the period where you're having the morning shoulder in the Pacific Northwest. So it's solving a grid problem, and it's also sopping up that excess backfeed from the solar. Here you can see the same thing. Obviously, there are some minimum requirements that water heater is going to need for maintaining water heat, so there is a small charge right here. But when we extended the window, even in the middle of winter, we can see mostly that snapback for the water heat was in periods outside of the shed command. And again, here we can see how that aligns with solar energy even in winter. Thank you for your time. I hope this stimulated some interesting thoughts about how to solve problems for building owners and how this is going to connect with how model predictive control and building level controllers need to solve customer problems, grid problems, and distribution grid problems, and how we can begin to innovate even our CTA-2045 at a more granular level on the building electrification and building decarbonization side. Thank you.
Thank you very much, Tanya. Appreciate that. Our next, I encourage you to enter any questions in the Q&A, and we'll answer those at the end of the session. But our next speaker will keep moving on. We'll hear from Tristan DeFranville. Tristan is CEO of SkyCentrics, a leader in open standards and smart building solutions that include CTA-2045, Open ADR. He has more than 20 years experience in software and hardware engineering management, including at Apple, SRI International. Tristan is on the Consumer Technology Association Committee managing the CTA-2045 standard, as well as working with NEEA, ACAAA, Energy Star, and national laboratories on Open ADR, Voltron, and other regulatory and policy issues, where his main focus is in enabling buildings and electric loads to support increased renewables on the grid. Tristan will speak a little bit more about CTA-2045. Tristan, I turn it over to you.
All right, thanks. First of all, it's an honor to be on the panel, and all of you out there attending, appreciate it. So I just hit the arrow and it didn't work. Okay, so I'm going to be going through some rich and dense slides. I won't be going over all the bullets. This is meant to be a resource afterwards. So just a reminder, it's nice not to have to tell so many people about CTA 2045 these days. But for those at Energy Star and the California Energy Commission and the utilities that are sort of wrestling with Open ADR versus CTA 2045 versus sort of an embedded Wi-Fi solution that came out of thermostats, which was the dream, wouldn't it be nice if everybody just bought smart things and made them available to utilities? unfortunately, nobody's very excited about having a mobile app access to their water heater. You know, they make sure it's the right temperature, and they don't think about it for 10 years. So that's the critical challenge we're facing with water heaters. And the CTA-2045 port means that instead of just the Wi-Fi that might have been put in by the OEM, you can choose cellular or smart meter mesh or FM radio. So you're essentially future-proofing that asset for life. You will always have access to it, which the utilities have rarely had. And finally, on the bottom, you can see that when necessary, the module or the cloud can support the water heater with OpenADR or DNP3 or 2030.5. So what are the communication path options that are available right now? Well, SkyCentrics makes Wi-Fi and cellular. We have OpenADR certified in the cloud. We could put it in the module. And then we were hoping to have AMI mesh modules. Unfortunately, COVID has put it into a challenge. But we certainly think that someday some of the companies that you see here would benefit from having a AMI mesh module as well, so that there's a guaranteed utility path. So this is a graphic that shows you on the left this sort of guaranteed utility path to that asset that Tanya just talked about. More than just water heaters, we need all loads to be flexible. And then, yes, this is an optional path for customer Wi-Fi that has been mentioned by Amruta. And, you know, some of the big OEMs are going to, of course, have a cloud, an Internet of Things cloud, and a mobile app. But the smaller OEMs are just happy to have a connection and don't have the resources necessarily to build their own cloud. So pretty picture of storage and how batteries get all of the glory, but of course demand response and essentially 24/7 flexible loads is starting to finally catch up, which we think is exciting. So let me tell you how CTA-2045 helps the machine stay really smart and deliver value to the customer. So what you're seeing here is this green line is the storage capacity, and you can see that right after a morning load up in purple right there, we loaded it up, the electric element came on, the storage capacity went to 0. So when the temperature is fully heated, the storage capacity is at 0. Then we shed it for the morning peak, it starts cooling off, it cools off all the way up to here, we load it for 20 minutes right before the evening shed. But then during the shed, look at this steep green line showing that there was a big water heater draw. And then the water heater itself, we didn't have to do this. It said, oh, I'm risking a cold water event. I'll come on briefly, even though it's during the shed event. So that's the cold water prevention algorithm. And these kinds of smarts can go into all the machines. So right now, this is field data. People are starting to see this graph more and more. This is electric resistance water heaters. I'm also going to show you the heat pump water heaters. So this was about 38 50-gallon water heaters averaged for every 24 hours, 1,440 minutes on the bottom here for 64 weekdays. So you can see the water heaters aren't being used much at night. They come on for morning shower snapback. They are used a little bit during the day, and there's another evening peak snapback that you're seeing. So obviously I colored the mauve and blue so that you could see how it goes to shift that load. Every day this can be shifted to work for supporting the grid. Now this is the time of use value that NRDC delivered and convinced the California Energy Commission to say, hey, see this time of use, we can shift when we shift water heater. But I'm now going to show you why I think it's critical to have more than time of use as quickly as possible. So here is the heat pump equivalent of the graph. Now, instead of 700 watt hours of the electric resistance, you're seeing a watt hour that's more close to 200 watt hours, this kilowatts right here. Well, no, sorry, that should be watts. And then a little bit less of an evening peak. And I'll show you some data that was presented last year where it's a little higher than that, maybe up to 300 watt hours. And then what you're seeing is the California ISO graph. So this was July 2019, one day. You can see that the duct curve in purple is where solar is added, and so that has the duct curve, still the morning peak. And then look at how the brown line of CO2 really matches the solar line, which makes sense, right? So now we're going to move, and you can see how the heat pump can do the same thing. Trim the morning peak, trim the evening peak, and go to wind power and solar power. Okay, and then here's the Josh Butzbaugh from PNNL presentation last year, and you can see these connected heat pumps providing 289 watt hours, so a little more value there. Now, this is the 1 day in every month of 2019 of that California ISO graph. So you can see that if time of use is traditionally seasonal, let's say 2 or 3 seasons per year, you're already getting a lot of variation here, not in the peak, that's happening at about the same time, not in the morning peak, but it's in the ramp, right? The ramp can start at either 9 or 10 in the morning versus 5 in the evening. So when you want to shift and fill in that ramp, that's what changes quite a bit. Where we think there's value to daily cellular communications or AMI communications rather than time of use. So here are the electric resistance green graph and the brown graph of heat pump, and you can see how shifting that over to the morning valley and trough, as was said, and the afternoon trough really has value. But the last thing is I'm going to show you how this was July 15th. You've seen that graph before. And July 15th, the beginning of the ramps at 9 in the morning, and then look at 7 days earlier. That is quite a different trough graph, right? The ramp starts at 4:30 in the afternoon, the valley's at 1:30, so there's a whole difference there, and that's why we believe that daily cellular communications and tweaking of the schedule has a lot of value. Let alone, what are you going to do when feeder stations have an inverse curve because of a different load shape, which we've seen also. So that was the old one that you'd seen before. So let me now shift over to some field installations that are happening. So cellular CTA modules are going on heat pump water heaters in Minnesota, Colorado, and Hawaii. Hawaii is doing something fascinating, which I think we should all be aware of. Hawaii had a $2,000 incentive for if you attached solar to one unitary residential water heater. This carport feeding 140 apartments is actually getting the water heater discount of $2,000 incentive by the state of Hawaii because our partner showed that this solar grid is controlling through our CTA-2045 module those water heaters. So instead of a direct connection, they just showed, hey, the entire system is shifting the electrons from the solar to the water heater. So that's a very exciting development that I think other states could follow on. Let's also talk about field installation of commercial skids. So yesterday, Mitsubishi presented, Sandon has presented in the past, and we're working helping Mitsubishi, Sandon, and others give a CTA port kit that can actually retrofit to their system controllers and give a CTA-2045 port so that we can plug in our cellular module. So imagine this kit's going on commercial building rooftops, and you plug in the kit, you plug in the cellular module, and you instantly have grid control. And we're also feeding about 200 points of data from the skid out to our cloud for delivery to Ecotope and others for really monitoring these new commercial heat pump systems. So that's really exciting, and we're excited about that. I also wanted to cover incentives. So everybody should know that California is trying to layer incentives so that there's up to $5,000 of incentives for the installation of one heat pump water heater in residential. Now that sounds like a lot, but there's incredible value there, and we're trying to do market transformation in California because there's 13 million gas water heaters right now that aren't going to support the grid in any way. And then for the commercial side, these are the layers of incentives that can build up to $11,000. That's exciting. Finally, I want to finish with some developments. So CTA-2045 is now going to be hosted on the OpenADR Alliance website. the qualified product list. So the confusion between OpenADR and CTA-2045 is going to be removed. CTA-2045, the test tool that's going to be delivered to UL and Intertech in March, next week, it's going out to all the OEMs and their water heaters, and we're going to have certified CTA-2045 water heaters and modules. And white papers are being released on how OpenADR and CTA-2045 work well together, but that it's critical to have the port in place. And then there's an exciting branding process because CTA-2045, like 802.11 before Wi-Fi, is not a great name, and we're looking, and there's going to be a vote next week at AWHI. There's been some great work done by OpenADR on surveying all the stakeholders to decide what should we call it, a grid port, an eco port, or lots of other options, and we'll find out next week which ones we're voting on. Finally, let's talk a little bit about CTA-2045-B Level 2. So it tried to incorporate the time of use schedules that NRDC and Title 24JA13 required, but it also added the end game for all of this, which is streaming prices to devices, wholesale prices, or at least retail electric prices, where all the loads can flexibly respond to support the grid in real time. Advanced load up has been discussed in other places, and then there's efficiency levels and user preference levels. And Tanya just talked about how it's critical for the user preference to say, hey, I really want to participate and lower my carbon as much as possible, or hey, I have the soccer team in place for the weekend and I'd like to have as much hot water as possible. And then the efficiency level signal allows utilities to say, hey, maybe we do want to use the electric element in that hybrid heat pump, so use as much energy as possible. Of course, there needs to be a way to offset the extra cost and the lost efficiency. This is an important one, CTA 2045.1. It allows us, through the module, to update the firmware on the appliance. This has already been really useful in the field to be able to add advanced load up to water heaters that were being installed after they were being installed. So this is an optional CTA 2045 standard, and utilities should always be asking to the OEMs, hey, do you support this so that we can upgrade features in the field in the future? Finally, CTA 2045.4 is going to provide local access. That's just starting. It'll probably be a year before that comes out. So I want to finish with the value of heat pump water heaters to the grid. We've extrapolated the data from a Massachusetts study, and just the 13 million water heaters in California, if they were electric, which is what the Water Heater Initiative is working on, they would be a value of $10 to $20 billion yearly to the grid and reduce California grid emissions by 6% per year. That's reducing 3.5 million cars worth of carbon every year. So there it is. We need to have grid-controlled water heaters through cellular, AMI mesh, FM radio, all of that flexibility that the CTA port gives you, because we want to avoid all those fires that you see that happened last summer on the West Coast. Thank you.
Thanks so much, Tristan. I really do appreciate it. So we'll move on to our final speaker. Speaker is Ebony Mayhorn. Ebony obtained a BS in mechanical engineering from Prairie View A&M University, and then continued on to Texas A&M, where she earned an ME in the same area. She also earned a PhD in electrical engineering with a focus in power systems at Texas A&M in August 2015. She joined PNNL as a research engineer in 2013, and her main focus has been on unifying industry on the vision and characteristics desired for connected buildings equipment to deliver both reliable grid and building services. In addition, she has worked on several other power grid-related projects, developing solutions to facilitate large-scale integration of clean energy resources with the power grid. Ebony will speak about load shifting strategies. So Ebony, turn it over to you.
Thanks, Bill. Hi, everyone. I'm going to speak with you about the recent field study that we held in the Northwest over the past few years. It's on the load shifting capabilities of heat pump water heaters with CTA 2045 communication protocols. As we've discussed previously with the other panelists, we know demand response or load shifting can be used to help align loads with renewable generation, and we can use that to also manage our peak loads in the systems. And what's needed here to do this at scale is really to quantify the values for the utilities and consumers, as well as to understand the customer acceptance for different control paradigms. And we know that CTA-2045 has some capabilities that are available that will allow us to have the ability to allow aggregators and utilities to choose the way that they want to communicate through like cellular, Wi-Fi, or through other options. We can also, or radio frequency. We also, it also allows different entities to talk with the devices, so it's not stranded assets at the end whenever there are changes in locations or territories. And we focus mainly on heat pump water heaters because they are the more efficient technologies that are trying to be promoted. There's been a lot of research and studies done on electric resistance water heaters that are well understood. And so our focus has been on heat pump water heaters. I believe they've kind of explained in the previous presentations how the CTA works, but I'll just briefly go through. In our field study, the water heaters were already installed with the 2045, the CTA 2045 ports. Then an aggregator like eRadio would provide a universal communication module so that we can communicate through RF or Wi-Fi. And once that's installed on the water heaters, now we can start to send curtailment commands or load up commands to be able to control the water heaters at the desired, based on the objectives or whatever the desired times are. So again, we were looking in the Northwest. So we had up to 147 water heaters included at any given time in our study. They were all equipped with the CTA 2045 communication module. They were all located in Portland. Most of the water heaters were about 50 to 55 gallons. Some had a little higher capacity. We looked at different load shifting commands, the direct commands like sending specific standard CTA 2045 control commands like load up, shed, critical peak, grid emergency. And then we also looked at indirect commands based on variable price signals. And there was 4 different strategies that we also looked at: non-targeted, targeted, and smart direct strategies. For the non-targeted and targeted, we discussed those in the Hot Water Forum on last year. But essentially, the non-targeted was an approach where we would just send the same signals all to the entire population of water heaters at a given time. For the targeted approach, we would split the water heater groups into high and low hot water users for both the morning and afternoon, and then we would send a different schedule to the different groups. And this was to just extract more shifting out of the entire group without having an impact to the higher users. So we would basically extend the shed or curtailment events for the lower hot water users. And then we looked at a so-called SMART. It's a third-party SMART algorithm that we decided to take a look at. And it's more of an individualized control where it was based on direct commands. So the same load up and shed signals that we could send, but this approach had two-way communication to optimize what those commands should be, and then also adapt the commands as needed whenever the storage limits are being approached for the water heaters. We also looked at a smart third-party indirect approach where the individualized control was based on price signals, and again, it incorporated the feedback to adapt the control commands. So this year, because we compared the non-targeted and the targeted approaches last year, this year we're really just looking at how the smart third-party algorithm could be used to provide greater shifting compared to those strategies that we looked at last year. And then we also wanted to know whether the more aggressive CTA-2045 curtailment commands like the critical peak and a grid emergency could also lead to greater shifting without homeowners noticing. Another question that we looked at was, can a smart indirect strategy lead to greater cost savings than a somewhat simple rule-based direct approach that is also based on variable price signals? So here are the results for the direct strategies. We split it into morning results and the afternoon results. So we considered a peak period of like 6 a.m. to 11 a.m. for the morning, and a peak period of 5 p.m. to 10 p.m. for the afternoon. And this table just summarizes the results for the non-targeted direct approach using simple shed commands, the targeted smart direct approaches using the simple shed commands, and then the smart approaches with the more aggressive critical peak and grid emergency commands. And you can see in each study how many water heaters were included. Over a certain amount of time, we started to lose water heaters from the study. And we can also see the event durations, the times where we sent the events, and then the number of weeks that we included in the summary of the amount of shifting that we got over those peak periods. And what we are able to see is that the smart direct strategy with the simple shed was able in the morning to provide a higher load shifting than the non-targeted and targeted approaches. And then as we increase the aggressiveness of the curtailment signals, like the critical peak and the grid emergency, we also saw at least 22% increase at each level. And for the afternoon results, again, we see that for the non-targeted versus targeted, we saw a greater load reduction than in the targeted versus the non-targeted. However, in this particular case, we didn't see that the smart performed better than the targeted approach. However, we were able to see as the commands became more aggressive, we did get more increase in shifting. And the reason why the smart approach didn't outperform the targeted approach in this particular case is because of the timing of when the shed events occurred for the high and low users. In this particular case, compared to the morning, the shed events ended at the same time. So the recovery started after the peak period. And in the morning results, and I'll just go back to it right quick, we can see that the high AM users, the shed event ended at 10 a.m. instead of 11 a.m. So the recovery started for that group before the end of the peak period. So then it caused the shifting to be lower here. And now looking at the indirect strategies using high price variability signals, we looked at two different high price variability signals with the the duct curves for New England ISO and the California ISO. And then, so you can see the two curves in the solid blue and green lines. And then for the dashed lines related to those specific price signals is the command signals that are generated by the third-party smart algorithm based on that variable price signal. And so what you can see here is that the smart algorithm either is deciding to shed or load up during the entire day. So this is a hourly signal over a day. And the only time that the devices will exit out of these commands is if it's reaching some type of storage limit on the on each one of the individual water heaters. And then we also looked at the smart indirect strategy, the same one for the New England ISO signal, which is in blue here. And then we compared it to a more simple direct strategy that is more of like a rule-based approach. And we considered two price thresholds in this case. And so the red here represents, again, the third-party smart commands that are generated as a result of that New England ISO signal. But then the black line here is the signals that are generated by the direct simple method. And so the dashed lines here represent the upper and lower price thresholds. And for the simple approach, we can see that whenever the price is above the upper threshold, then the commands are to shed. If it's in between those two upper and lower thresholds, then there's no command sent. And then if the price is below the lower threshold, the command is to load up. And so this just shows the differences between how the smart algorithm generates the commands versus the simple direct approach. And here are the preliminary results for that. We couldn't really make general conclusions about the results that we obtained because we only considered about 10 water heaters in this study. And we only had about a week, or in some cases, less than a week of data to really compute the cost savings. But however, when we're looking at the Cal ISO and the New England ISO signal for the third-party smart indirect method, we saw over 25% in average cost savings. And then for the New England ISO direct approach, the simple direct approach, we got less than 10%. So here we actually are seeing so far, smart strategy has the ability to reduce the cost. So in conclusion, we saw that the targeted approach could yield a greater load shifting than smart strategy if the timing of the low and high user events are at the same, or they end before the peak period ends. I mean, after the peak period. And we also see that the more aggressive CTA curtailment commands like grid emergency can lead up to 42% more than the shed commands. However, we did notice in a few cases, which is why we used 10 water heaters in the more recent study, we had to remove some of the water heaters from the pilot because we got some complaints when we were implementing the more aggressive commands from one of the manufacturers. So we eliminated those from the study. So with that said, we need to make sure that the appropriate local controls are implemented so that we can avoid those cold water events, even if we're sending aggressive signals to the device. So the water heater can just exit out of those commands if there's a threat for cold water events. And we saw that the smart strategies could lead to greater cost savings when considering price signals or indirect signals, but more investigation is needed here. So that's all I have for today. Thank you.
Thanks very much, Ebony. We do really appreciate it. So as you can see, we're trying to jam in these 4 presentations, so we don't really quite have any time to answer the Q&A here. But what I want to say is that we do have the Zoom link that is available. We'd love to continue this conversation with everybody in the link. And there's already in the Q&A, some of the speakers have already responded to them. But we do encourage everybody to join us over at the Zoom link so we can continue this conversation, these 4 great presentations. So thank you, everyone, and we'll see you soon in the Zoom link. Bye-bye now.